Okay, so good day everyone. Our topic for today is about round robin, which is the type of CPU scheduling under operating systems. Okay, so what is round robin scheduling? The name of this algorithm comes from the round robin principle, which are persons gets an equal share of something in turns. It is the oldest, simplest scheduling algorithm, which is mostly used for multitasking. In round robin scheduling, each ready task runs turn by turn only in a cyclic queue or a limited time slice. And this algorithm also offers starvation-free execution of processes. So this will be the characteristics of round robin scheduling. So it is a hybrid model which is clock driven. Time slice should be minimum, which is assigned for a specific task to be processed. However, it may vary for different processes. It is a real-time system which responds to the event within a specific limit. Okay, so this will be an example of a round-robin scheduling, turnaround time and waiting time. So consider the following set of processes that arrive at time zero with the length of the CPU burst given in milliseconds. In time quantum takes as 4 milliseconds for round-robin scheduling. So to give us a discussion, let us please watch the video from NES Academy.
So here we are given a set of three processes with process IDs P1 to P3 and their burst times are given in milliseconds. So P1 has a burst time of 24 milliseconds, P2 of 3 milliseconds and P3 also of 3 milliseconds. And we assume that all these processes arrive at time 0. So the arrival times for processes P1 to P3 is time 0 and the time quantum is taken as 4 milliseconds and it follows a round robin scheduling. So if you remember what I taught in the previous lecture about round robin scheduling, we have seen how it works. So there we saw that in round robin scheduling, we have a particular time quantum, which is a particular amount of time that will be assigned to each processes for their execution. So a particular process will be allowed to use a CPU for a particular quantum of time that we define, and once that time period expires, the process will be preempted and the next process in queue will be given the CPU for its execution, which will also be allowed to use the CPU for a particular time quantum, and then it will be preempted and the next process will be given the CPU and so on. So that is how a round robin scheduling works, which we have explained in detail in the previous lecture. So here in this example that we are taking, the time quantum is 4 milliseconds. That means each of the processes will be allowed to execute for 4 milliseconds. And after that, the CPU will be given to the next process in the queue, which will also be allowed to use a CPU for 4 milliseconds. And then that will be preempted and so on. So here the time quantum is 4 milliseconds. So here we will be seeing how we can calculate the turnaround time and waiting time for this set of processes. So the first step in calculating this turnaround time and waiting time for any scheduling algorithm that we have is to first form the Gantt chart. So we have to form the Gantt chart for this set of processes, and after that we will be proceeding to calculate the turnaround time and waiting time. So let us see how we can form the Gantt chart for this. So here I have shown how the Gantt chart will be formed and I will be explaining this, but before that keep in mind that here we are following round robin scheduling and we are to consider the time quantum which we have, and the time quantum is 4 milliseconds. So 4 milliseconds is our time quantum, keep this in mind. So we know that all these processes P1 to P3, they arrive at time 0. So they are waiting in this order, P1, P2, P3 in the ready queue. So P1 is the first one that we have, and P1 will get the CPU at the 0th millisecond. So when P1 gets the CPU, it has to execute for how long? The burst time of P1 is 24 milliseconds. But will it be allowed to execute for 24 milliseconds? No, because this is round robin scheduling and we have a time quantum and it will be allowed to execute only for that particular period of time, which is 4 milliseconds in this case. So P1 will be executed for 4 milliseconds. So from 0 to 4 milliseconds, P1 executes. And after that, what will happen? P1 will be preempted and the CPU will be given to the next process in the queue. So which is the next process in the queue? It is P2. And what is the burst time of P2? P2's burst time is 3 milliseconds. So at the 4th millisecond, P1 is preempted and P2 now gets the CPU. Now P2 also will be allowed to execute for 4 milliseconds, which is the time quantum. But we see that the burst time of P2 is only 3 milliseconds. It is less than the time quantum. So it will execute only for 3 milliseconds. So P2 executes for 3 milliseconds, which is from 4 to 7. So at 7 milliseconds, P2 will voluntarily release the CPU because its burst time was only 3 milliseconds, which is less than the time quantum. So we don't have to preempt P2, but it will voluntarily by itself release the CPU. Now at 7 milliseconds, the CPU will have to be assigned to the next process in the queue. So which is the next process? It is P3. So P3 gets the CPU at 7 milliseconds. And how long it has to execute? It has to execute for 3 milliseconds. So again we see that the burst time of P3 also is less than the time quantum of 4 milliseconds. So P3 executes from 7 to 10, that is for 3 milliseconds, and it will also voluntarily release the CPU by itself. So at the 10th millisecond, P3 finishes its execution, and if we look here, there are no more processes here. But what actually happened was that P1, it only executed for 4 milliseconds, that is for the time quantum, but it still has to execute for 20 more milliseconds because only 4 milliseconds was executed. So if we subtract 4 from this 24, which is the burst time of P1, we see that it has a remaining burst time of 20 milliseconds. So it has to execute for 20 milliseconds more. So what happened was that when P1 was allowed to execute for 4 milliseconds here, and at the time it was preempted, P1 was taken and put at the end of the queue. So the queue looked something like P2, P3 and P1 because P1 is again coming at the end of the queue. So when P3 completes its execution, there is P1 still waiting at the end of the queue. So P1 will have to be given the CPU. So P1 will get the CPU when P3 releases it, and it will be executed for how long? We see that it will be executed only for the time quantum of 4 milliseconds. So P1 executes from 10 to 14 milliseconds. Now did P1 complete its execution now? No, P1 has not completed its execution. Let's see how much did P1 execute. P1 executed for 4 milliseconds here. Then here P1 executed for another 4 milliseconds, which is 4 plus 4, 8 milliseconds. So P1 still has a remaining of 16 milliseconds to execute. So P1 is still there in the queue. So at the 14 millisecond, P1 will again be preempted because that is the way round robin scheduling works. After the time quantum of 4 milliseconds, the currently executing process has to be preempted. But we see that there are no other process other than P1 in the queue. So it will be P1 being preempted and P1 itself being given the CPU in this case. So at the 14 millisecond, P1 gets preempted, and again P1 will be given the CPU because there are no other processes waiting in queue other than P1. So P1 will again execute for 4 milliseconds, which is 14 plus 4 up to 18 milliseconds. Now did it complete? No, it did not complete. Now P1, how much did it execute? Here we see 4, here another 4, here another 4. So a total of 12 milliseconds were executed. And there is a remaining of 12 milliseconds that P1 has to execute because the total burst time is 24 milliseconds. So again P1 gets preempted here, and again P1 itself gets the CPU here. So from 18 to 22, that is for 4 milliseconds, it executes again, and then here again P1 gets preempted, and again P1 gets the CPU and it executes for 4 milliseconds, and again the same thing happens here. So from 26 to 30 milliseconds, P1 will do its final execution. So if you see, the burst time of P1 is 24 milliseconds and it executed here for 4 milliseconds, plus 4 here 8, and plus 4 here again, that gives us 12, and if you plus 4 here again, that gives us 16, and if you plus 4 here again, that gives us 20, and if you plus 4 here again, that gives us 24 milliseconds. So that is how P1 completes its execution at the 30th millisecond. So here we see that each process is allowed to execute only for the time quantum of 4 milliseconds. So at the end, even though it was only P1 that was waiting in the queue, P1 will execute only for its 4 milliseconds, then it will be preempted, but since it was the only process in queue, P1 itself will be given the CPU and it was executing again and again. So that is what happens in a round robin scheduling. So if there are more processes, you can do the same thing, and remember that a process that is preempted will be always put at the end of the queue. So all the processes will be executed, and the process that is preempted will always be put at the end of the queue. So keep that in mind, and then you will be able to easily form the Gantt chart for this. Alright, now we have formed the Gantt chart, and now let's see how we can calculate the turnaround time and the waiting time for round robin scheduling. So I've copied down the same table here which shows our process IDs and the burst time and the Gantt chart that we have formed just now. So now let's see how we can calculate the turnaround times and waiting times. So for this round robin scheduling, there are two methods in which we can calculate the waiting times. So let's see what are those two methods. So the first method is using the formula that we have used for even the other scheduling algorithms. That is, turnaround time is equal to the completion time minus the arrival time. And then the waiting time will be the turnaround time minus the burst time. So from the completion time, that means when the process completely finishes execution, from there if we subtract the arrival time, we'll get the turnaround time. And from the turnaround time that we just calculated now, if we subtract the burst time, then we will get the waiting time. So this method will be useful when you have to calculate both turnaround times and waiting times for a set of processes. So let's see how we can calculate the turnaround and waiting times using this formula for this set of three processes. So here I have a table where I have shown the process with process IDs P1 to P3, and here we have the completion times of each of these processes. So to see the completion times, we can just look at the Gantt chart and find it out. If you see for process P1, when did it completely finish its execution? So we see that P1 completely finished its execution over here at the 30th millisecond. So that is the last occurrence of P1 in the Gantt chart. So that will be the completion time, that is 30 milliseconds. Now for P2, when did it last occur? It was here. And what was the time it completed? 7 milliseconds. So 7 is the completion time for P2. And for P3, similarly, it last occurred here, and this is where it completed its execution. So 10 milliseconds is the completion time of P3. Now let's calculate the turnaround time. So the turnaround time for P1 will be the completion time minus the arrival time. So what is the completion time? It is 30 milliseconds. Now what is the arrival time? In the question, it was already given that all these processes arrived at time 0. So they all arrived at 0 milliseconds. So the arrival times are 0 for all the processes that we have here. So the turnaround time of process P1 will be 30, that is the completion time, minus 0, which is 30 milliseconds. Now similarly for P2, what will be the turnaround time? It is the completion time 7 minus 0, which is 7 milliseconds. And similarly for P3 also, the turnaround time will be the completion time 10 minus the arrival time 0, that is 10 milliseconds. Alright, so we can easily calculate the turnaround times like this. So in this question, the arrival times were all 0. So in some other problems, you may have different arrival times. So if you are having different arrival times, then use the arrival times as given in the problem. Alright, now we can calculate the waiting time. So the waiting time is the turnaround time minus the burst time. So turnaround times we just calculated here, and the burst time is what is given in this table. So for process P1, the waiting time will be the turnaround time 30 minus the arrival time 24, which is 30 minus 24, 6 milliseconds. And for P2, the waiting time will be the turnaround time 7 minus the burst time of 3, which gives us 7 minus 3, 4 milliseconds. And finally for P3, the waiting time is turnaround time 10 minus the burst time of 3. So that gives us 10 minus 3, that is 7 milliseconds. So here we have calculated the waiting times as well. So you can use this method when you have to calculate both turnaround times and waiting times. So you can calculate turnaround time like this, and once you have calculated turnaround time, you can easily calculate the waiting time. So now we'll go to the second method, and in this method we will calculate only the waiting times. So this method will be useful if you have to calculate only the waiting time and you don't have to bother about the turnaround time. So here the formula that we have is waiting time equals last start time minus the arrival time minus preemption into time quantum. So this formula may look long, but it is very easy. Let's explain it. So last start time means the last time that the process started its execution. So for example, for P1, we see that P1 started its execution here at 0 milliseconds. But was this the last start time? No, because P1 again started execution here at 10 milliseconds, and here again at 14 milliseconds it started, then again at 18 also it started, then 22, 26 also it started. So we see that the last start time of P1 was 26 milliseconds. This is the last time it started. So when it started at this 26 milliseconds, it completed this execution at 30th millisecond, and after that it did not start again. So 26 is the last start time for P1, and from that we have to subtract the arrival time. So for this example, the arrival times are 0 for all the processes, and then from there we have to subtract the preemption into time quantum. So preemption means the number of times the process got preempted. So how many times did P1 get preempted? Let's see. So P1 got the CPU here and it was preempted and the CPU was given to P2. Then again here we see P1 got the CPU and it was preempted and it was again given to P1. So from here also it was again preempted, and from here also it was preempted, and from here also it was preempted. Now when it got the CPU here for the last time, at this point of time it completed its execution, so there is no preemption happening here. So how many times did P1 get preempted altogether? 1, 2, 3, 4, 5. So P1 got preempted 5 times. So similarly you can check for other processes. So preemption, so here the preemption value is 5. The number of times the process got preempted. So for P1 it is 5 into the time quantum. So with that you have to multiply the time quantum. So our time quantum was 4 milliseconds in this example. So 5 into 4, you have to multiply that. So when you apply this whole formula, you'll get the waiting time for a particular process. So let's see how we can do this. So for process P1, what is the last start time? The last start time is 26 milliseconds, as I already explained. This is the last time it started. So look at the Gantt chart and look for the last occurrence of that particular process and see what was the start time. So that is the last start time. 26 minus the arrival time. So we know that the arrival times are all 0 milliseconds for this set of processes. So it is 0. Then from there we have to subtract preemption into time quantum. So how many times did P1 get preempted? I just showed you that it got preempted 5 times. So 5 into the time quantum, which is 4 milliseconds. So into 4. So what is the value that we'll get here? 26 minus 0 minus 5 into 4. So if you multiply 5 into 4, we get 20. 5 fours are 20. So 26 minus 20 is 6 milliseconds. So that is the waiting time for P1. So if you see here also we got the same thing, 6 milliseconds for P1. So similarly, let's calculate for P2. So for P2, what is the last start time? The last start time for P2, where is it? It is here. So if you see in the Gantt chart, P2 occurred only one time. So this is the first and last start time for P2. So 4 is the last start time for P2, and then the arrival time is 0, and then preemption. So how many times did P2 get preempted? We see that P2 was never preempted. P2 got the CPU once and it completed its execution at that time itself. So there is no preemption for P2. So the preemption is 0. So multiplied by the time quantum, which is 4 milliseconds. So that is 0 into 4. So 4 minus 0 minus 0 into 4 gives us 4 milliseconds. So finally for P3, we see that the last start time of P3 is 7 milliseconds. So P3 also got the CPU just once and it completed its execution that time itself. So this is the first and last start time. So 7 is the last start time for P3, and then the arrival time, as we know, is 0, and the preemption. So we see that P3 also was never preempted. So it is 0 into the time quantum, which is 4 milliseconds. So 7 minus 0 minus 0 into 4. So that will give us 7 milliseconds. So if you compare here and here, we see that in both the methods, we are getting the same answer. So this first method can be used when you have to calculate both turnaround time and waiting times, and the second method can be used if you only want to calculate the waiting times. So that is how you calculate the turnaround time and waiting times. Now let's see if we can find out the average turnaround times and waiting times for these two methods for this set of processes. So here we calculate the average turnaround time and waiting times. Average turnaround time for this set of processes were 30 plus 7 plus 10 divided by the number of processes, that is 3. That gives us 47 by 3, that is 15.66 milliseconds. And the average waiting time is 6 plus 4 plus 7 divided by the number of processes 3. That gives us 17 divided by 3, that is 5.66 milliseconds. So similarly for this second method also, it is the same thing. Average waiting time 6 plus 4 plus 7 divided by 3, that gives us 5.66 milliseconds. So in most of the problems, you may be asked to calculate the average turnaround time and the average waiting times. So if you have to calculate both of them, you can use the first method, or if you have to calculate only the waiting time, you can use the second method. So that is how you calculate the turnaround time and waiting time for round robin scheduling. So form the Gantt chart carefully and apply these formulas, and you can easily calculate it. And also we see that in this round robin scheduling, the waiting times may be a little longer as compared to other algorithms, because this algorithm is mainly used for time sharing systems, and we have to carefully define the time quantum, because if the time quantum is too long, this round robin scheduling will become like a first come first serve scheduling, and it is not useful. And if the time quantum is too short, then there will be too many context switches happening. So we have to strike a balance between the two in order to maintain the efficiency of this algorithm. So I hope this was clear to you. Thank you for watching, and see you in the
Okay, so this time I will give you an additional problem with solutions from Neso Academy about round robin scheduling.
we are given a set of 5 processes with process IDs P1 to P5, and their arrival times are given here and the burst times are given here. So we are required to find the average waiting time and the average turnaround time if the scheduling policy is round robin and the time quantum is 2 units. So this is a little bit different from the previous example that we have discussed in the previous lecture, because in the previous lecture the arrival times were not given, and it was assumed that all the processes arrived at the same time. So it was a bit easy to calculate. But in this example, or in this problem, the arrival times also are given for this set of processes. So we have to keep in mind these arrival times, and there are many things that we have to keep in mind and be very attentive when we are solving this problem of this kind. So this is going to be a bit lengthy, because I am going to explain in detail about how it works. So that is why I have divided this lecture into 2 parts. So in this first part, we will be seeing how we can form the Gantt chart for this set of 5 processes, which is the most crucial step. And in the next part, we will be calculating the average waiting time and the average turnaround time. So keep in mind that this is a round robin scheduling, and we know that in round robin scheduling, each process is allowed to execute for a particular time quantum, which is 2 units in this case. And after the time quantum, the process will be preempted. After that, the CPU will be given to the next process waiting in the queue, and this pattern continues. So that is what happens in round robin scheduling. So since the arrival times also are given here, there are many things that we need to keep in mind, and we have to solve it very attentively. So it is not very difficult, but you have to be very careful. So let's see how we can form the Gantt chart for this set of 5 processes. So I've copied down the same table over here, and here keep in mind that the time quantum is 2 units, and here I am having a clock which will help us to keep track of the time and see what happens at different time units. So you don't have to draw this clock and all when you are really solving the problem, but in order to make you understand, I am taking this example. So let's see how the Gantt chart can be formed. So here I have formed the Gantt chart for this set of processes, and don't worry looking at this, I am going to explain it in detail. And also we are having a ready queue here. So in this ready queue, we will be putting the processes that are coming and waiting in the ready queue. So that will be represented here. So remember that this right hand side will represent the head of the queue, and the left hand side will be the tail of the queue. So when the first process arrives, it will be kept here, and when the second process arrives, it will be kept behind that, and when the third process arrives, it will be kept behind that, and so on. So that is what we mean by the head and the tail of the queue. So let us see how all these things work. So first of all, let's look at this table and let's see what happens at different units of time. So in this clock, we will be starting from the 0th unit of time. So at time 0, let's see what happens. So at time 0, the process P1 arrives. So here we see that P1 is the first process to arrive. So P1 is the process that comes and waits in the ready queue, because it is the first process and it is ready to be executed. So at time 0, process P1 comes and it is ready to be executed. And since there were no other processes at this time, so what will happen? P1 will be given the CPU. So P1 will be now coming to our Gantt chart, which shows that it got the CPU and it has begun its execution. So we can remove P1 from the ready queue, because in the ready queue, the processes will be there when they are waiting for the CPU. But once they get the CPU, they will not be in the ready queue anymore. So P1 is removed from the ready queue and it is now continuing its execution in the CPU. Now let's see what will happen next. So here we were at time 0. Now let's go to the next unit of time. So the next unit of time is time 1. So let's see what happens at time 1. So at time 1, P1 is still continuing its execution. We know that the time quantum is 2 units. So P1 has not completed 2 units. It is still within the time quantum of 2 units because we are just at time 1. So P1 continues its execution. Now let's see what happens in this table. So in this table we see that at time 1, P2 has arrived. So P2 is arriving at time 1, but it cannot be given the CPU at this time because P1 is currently using the CPU and has not completed its time quantum of 2 units. So what will happen? P2 will be placed in the ready queue. So we have P2 in our ready queue now. So that is all that happens at time 1. Now let's see what will happen at the next unit of time. So the next unit of time is time 2. So at time 2 what happens? There is an alarm ringing. So why does the alarm ring? The alarm rings because we know that the time quantum is 2 units. So the ringing of his alarm signifies that the time quantum has ended and it is time to preempt the currently executing process, and it is time to give the CPU to the next process waiting in the ready queue. So that is what we have to do. So at time 2, P1 will be preempted and P2 will be given the CPU because P2 is the process that is waiting at the head of the ready queue. So that is what we have to do at time 2. Now when P1 is preempted, what is the remaining burst time of P1? Even that we have to keep in mind. So the burst time of P1 is 5 units of time, and here it has executed for 2 units of time. So there is a remaining of 3 units of time that P1 needs to execute. So P1 has not completed its execution. So keep that in mind. And since P1 has also not completed its execution, P1 will also be now placed in the ready queue. So shall we place P1 here? Wait, before we place P1 here, let us also look if there were any other processes that has arrived at time 2. So if you see the table, we see that P3 also has arrived at time 2. So P3 will be placed at the ready queue, and after that, this P1 which was preempted will be placed behind that. So P2 will be now removed from the ready queue because it is now going to get the CPU for its execution. So let's remove P2 and place the other 2 processes. So this is what our ready queue looks like now. P2 got the CPU and is going to begin its execution, and P3 which has arrived at 2 units of time is placed at the head of the ready queue, and P1 which was preempted now and has a remaining burst time of 3 units of time is placed behind P3 at the ready queue. So this is what happens at time 2. So P2 will now begin its execution. Now let's see what will happen at the next unit of time. So the next unit of time is 3 units. So at 3 units, let's see what happens. So at 3, P2 is still continuing its execution because it has not yet completed 2 units. It can actually execute from 2 to 4 units of time. So at time 3, P2 is still executing. And let's see our table, what happens in this table. We see that there is a new process P4 that has arrived at time 3. So at 3 units of time, P4 has arrived and P4 has to be placed at the ready queue because right now this Gantt chart cannot be disturbed because P2 is executing and it has not completed its time quantum. So P4 will now be placed at the ready queue. So P4 is now placed at the tail of the ready queue, and this is what our ready queue looks like at time 3. Now let's see what will happen at the next unit of time. So the next unit of time is time 4. So at 4 unit of time, what happens? The alarm rings again. Why did the alarm ring? Because the time quantum of 2 units are complete. So from 2 to 4, the clock ran and that was 2 units of time. So the alarm rings, which signifies that the process that is currently executing should be preempted and the CPU should be given to the next process waiting in the ready queue. So which was the process executing? It was P2. P2 was the one using the CPU, and at time 4, P2 has to be now preempted and the next process should be given the CPU. So now which is the next process that should be given the CPU? We have to see the ready queue. So in the ready queue, P3 is at the head of the ready queue. So P3 will be given the CPU and P2 will be preempted. Now when this happens, what is the remaining burst time of P2? Let's see. The burst time or the total burst time of P2 is 3 units of time, and it has executed for 2 units here. So there is a remaining of 1 unit. So P2 has a remaining of 1 unit of time which has to be executed later. So P2 also has to be placed at the end of the ready queue. But let's see if that is the case or if there were any other processes that arrived at time 4. So if you see at time 4 there is another process P5 that has arrived. So P5 also has to be placed at the end of the ready queue. So what we'll do is we'll first place P5 at the end of the ready queue, and behind that we will be placing P2 which was preempted. So always remember that the process that is preempted will always be the last one in the queue. So we'll first place P5, then P2, and P3 is the one getting the CPU and going to begin its execution. So we can remove P3 from the ready queue. So this is what our ready queue will look like now. P3 is taken from the ready queue and it's put in the Gantt chart because it is using the CPU for its execution, and P5 which has arrived at time 4 is kept at the ready queue, and P2 which is preempted is also kept at the end of the ready queue. So this is what happens at time 4. Now let's see what will happen at the next unit of time, that is 5 units. So at the 5th unit of time, let's see what is happening. So if you look at the Gantt chart, P3 was a process that was executing. Now P3 got the CPU at 4 units at the previous unit. And what is the burst time of P3? The burst time of P3 is only 1 unit of time. So it does not have to use for the total 2 units, that is the time quantum, but it only has to use for 1 unit of time. So at time 5, P3 will complete its execution and it will voluntarily release the CPU, and the CPU will be given to the next process in the queue, that is P1. P1 is at the head of the queue, so P1 will be the one to get the CPU. So here the alarm is not going to ring because the time quantum of 2 units were not complete, and the burst time of P3 was only 1 unit of time, which is less than the time quantum. So P3 voluntarily releases the CPU and then gives the CPU to the next process in the queue, that is P1. So we can remove P1 from the ready queue and put it in the Gantt chart again. So P1 is now getting the CPU and it's continuing its execution. So how long does it have to continue? It can continue for only 2 units, but also remember that it has a remaining of 3 units of time. So P1 continues its execution, and let's see what happens in the next unit of time. So the next unit of time is 6. So at the 6th unit, what happens? There are no new processes that are arriving, and P1 is using the CPU, and P1 needs to use it for 3 units of time, but is allowed for only 2 units, which is the time quantum, and the time quantum is also not yet expired because P1 started its execution at 5 units and it will actually be allowed to execute up to 7 units. 5 plus 2 is 7. So at the 6th unit of time, nothing much happens. It's just P1 continuing its execution and these processes still waiting in the ready queue. Now let's go to the next unit of time. Now the next unit of time is 7 units. And at 7 unit, the alarm rings. Now why does it ring? Because P1 was using the CPU for 5 up to 7. 2 units, that is the time quantum, is complete. So the alarm rings notifying that the present process has to be preempted and the next process should be given the CPU. So P1 will now be preempted and the next process, that is P4, will be given the CPU because P4 is the one at the head of the ready queue. So that is what will happen. Now did P1 finish its execution? Let's see. P1 had a remaining burst time of 3 units of time, but it has executed only for 2 units here. So still there is a remaining of 1 unit of time that P1 needs to execute. So P1 will again be put at the end of the ready queue because it still has to use the CPU. So P4 we can remove it from the ready queue now because it will get the CPU here, and P1, which was preempted, will be kept at the end of the ready queue. So this is what our ready queue looks like now. P4 is taken from the ready queue and put into the Gantt chart because it is going to begin its execution, and P1, which was preempted, is put at the end of the ready queue. So P4 now begins its execution and it will have to execute for how long? The burst time of P4 is 2 units of time. So anyway, let's see what will happen at the next unit of time. So the next unit of time is 8, and at 8 we see that there are no processes newly arriving, and also the present process that is executing is P4, which has to execute for 2 units of time, and at the 8th unit of time it has completed only 1 unit of its execution and it has to execute for another one more unit of time. So there is nothing much happening here. It is just P4 doing its execution and these processes waiting in the queue. So let's go to the next unit of time now. So at the next unit of time, that is at the 9th unit, the alarm rings again. Why? Because the CPU was used from 7 to 9 units, that is 2 units here. So the time quantum is complete and the alarm rings, and the process that was using the CPU, that is P4, has to be preempted. So if you see here, we also see that the burst time of P4 is also 2 units of time. So even though it is not preempted also, it was going to release the CPU anyway after 2 units of time. So P4 has completed its execution and P4 will release the CPU now, and the CPU will be given to the next process. And what is the next process? The next process is P5. So P5 is the one waiting in ready queue now. So P5 will be given the CPU and the remaining process here will continue to wait at the ready queue. So P5 is removed from the ready queue and it is now in the Gantt chart beginning its execution. So remember, P5 also needs to execute for 3 units of time, that is its burst time. So the other processes, P3, we see that P3 already completed, and P4 also we saw that it already completed. So let's just strike them out. So at time 9, what will happen? P5 got the CPU and it is beginning its execution. So now let's go to the next unit. So the next unit is 10. At 10 units of time, what happens? We see P5 is continuing its execution. It is still within the time quantum, so there is nothing new happening. P5 is continuing its execution and there are no other processes that arrives. So nothing much is happening, only P5 is continuing its execution at time unit 10. So let's proceed to the next unit. So the next unit of time is 11. So at the 11th unit of time, the alarm rings again. Why? Because the CPU was used from 9 to 11, that is 2 units, that is a time quantum. So the alarm rings notifying that the present process has to be preempted. So which was the present process? It was P5. So P5 will be preempted and the CPU should be given to the next process in the ready queue, and which is that? It is P2, which is at the head of the ready queue. Now P5, did it complete its execution? No, because the burst time of P5 was 3 units of time and it has only executed for 2 units. So there is a remaining of 1 unit that P5 has to execute later on. So P5 will be put at the end of the ready queue and P2 will get the CPU, so P2 can be removed from our ready queue. So this is what our ready queue will look like now. P2 went here to the Gantt chart and P5 that was preempted is kept at the end of the ready queue. So at time 11, P2 that got the CPU now will begin its execution. So let's see what will happen at the next unit of time. So the next unit of time is 12 units. So at 12 units, what happens? So at 12 units, we see that P2 was executing and we see that P2's remaining burst time was only 1 unit of time. So from 11 to 12, P2 executed and it took less than the time quantum. So there is no alarm going off, but P2 has completed its execution and will voluntarily release the CPU. So P2 here has completed its execution. Alright, so what is the next process? The next process is P1 that is waiting at the head of the ready queue. So P1 will now be given the CPU. So P1 is removed from the ready queue and put in the Gantt chart because P1 gets the CPU for its execution. And let's see what will happen at the next unit of time now. So the next unit of time is time 13. So what happens at time 13? Who was using the CPU? P1. And what was the remaining burst time of P1? It was only 1 unit of time. So P1 executes for 1 unit and at the 13th unit it completes its execution. So the execution of P1 is complete and it took less than the time quantum of 2 units. So there is no alarm going off in our clock. So P1 will voluntarily release the CPU at the 13th unit of time and will give the CPU to the last process that is waiting in our ready queue, that is P5. So P5 will now get the CPU at the 13th unit of time. And how long it has to execute? It has to execute for only 1 unit. So P5 is removed from the ready queue and it comes to the Gantt chart and it gets the CPU for its execution. So at the next unit of time, that is at the 14th unit, P5 will complete its execution because it has a remaining burst time of only 1 unit of time. So P5's execution is also complete at the 14th unit of time and there are no more processes waiting in the ready queue, which signifies that all of the processes has completed their execution. So even if you look at this table, we see that there are no more processes that needs to be executed because all their burst times are complete and there are no processes in the ready queue. So at the 14th unit of time, all of the processes completed their execution. So this is how you can form the Gantt chart for a set of processes that follow round robin scheduling and when the arrival times are given. Given in the sense when there is a different arrival time. So when they are having the same arrival time, you don't have to keep these many things in mind. But when the arrival times are different, you need to keep all these things in mind. So keeping all these things in mind, if you can form the Gantt chart, then the rest of the process will become very easy. So I hope this formation of Gantt chart for this round robin scheduling when arrival times are given is clear to you. So thank you for watching, and in the next part, we will be calculating the average waiting time and the average turnaround time.
Okay, this will be the continuations of the discussions from NESO Academy about round robin.
Turnaround time for the set of processes. So let's go ahead and see how we can do that. So this was the Gantt chart that we have formed in our previous lecture. So we saw that the processes were preempted after completion of the 2 units of time, which was a time quantum, and then it was given to the next process. And if the process that was currently executing did not complete its execution, it was kept at the end of the ready queue and was given the chance again when its turn arrived. So this process was continued, and using that we have formed this Gantt chart where the process P1 started its execution at time 0, and then the last process to execute was P5, which completed its execution at 14 units of time. Alright, so with this Gantt chart, now we will be calculating first the turnaround time and then the waiting time for all these processes one by one, and then we will calculate the average turnaround and the average waiting times. So let's see how we can do that. So here are the formulas that we have already discussed before, and using these formulas we'll be calculating. So the turnaround time is calculated like this. It is the completion time minus the arrival time. So the completion time can be found from the Gantt chart. We just have to see the last occurrence of each processes, and then that will give us the completion time. For example, for P1, let's see where did P1 occur the last. So P1 occurred here, here, and also here. So this is the last occurrence of P1. And when did it complete? 13. So 13 is the completion time. So that is how you find the completion time from the Gantt chart. And then we need the arrival time. So for arrival time, we need our table. So here I will paste our table so that from here we can find out the arrival times for each of these processes. Then the waiting time is calculated like this. The turnaround time which we just calculated using this formula minus the burst time which can be found from this table. So using this, let's calculate all these things for this set of processes. So here I have formed the table in which we will be filling up these values. So we have processes with process IDs P1 to P5, and the completion times, as I already told you, we can fill up using this Gantt chart. So for P1 I already explained it is 13. So for P2, what is it? Let's see the last occurrence of P2. Where did P2 occur the last? Here. So what is the completion time? It is 12. So 12 is the completion time of P2. And for P3, where is the last occurrence? P3 occurred first and last just here. So the completion time of P3 is 5 units. And for P4, what is the completion time? Where is the last occurrence of P4? It is here. This is the first and last occurrence of P4 as well. And the completion time is 9 units. Now for the last one, P5, what is the completion time? We see that P5 occurred here and also here. So this is the last occurrence of P5, and the completion time of P5 is 14 units of time. So this is the completion time of P5. So using this completion times, let's calculate the turnaround time. So turnaround time is the completion time minus the arrival time, which we will see from this table. So for process P1, the completion time is 13 minus the arrival time, that is 0. So the turnaround time is 13 minus 0, that is 13 units. And similarly for P2, what is the turnaround time? Completion time 12 minus the arrival time, that is 1. So that gives us 12 minus 1, that is 11. And for P3, the completion time is 5 and the arrival time is 2. So that gives us 5 minus 2, that is 3 units. And for P4, the completion time is 9 and then the arrival time is 3. So that will give us 9 minus 3, that is 6 units of time. And for P5, the completion time is 14 and the arrival time is 4. So that will give us 14 minus 4, that is 10 units of time. So we have found the turnaround times for processes P1 to P5. Now using this turnaround time, we can now calculate the waiting time. So what is the waiting time? Turnaround time minus the burst time. Turnaround time that we found here minus the burst time given in this table. So let's see. For process P1, turnaround time is 13 minus the burst time, that is 5. So that will give us 13 minus 5, that is 8 units of time. And for P2, the turnaround time is 11 minus the burst time 3. So that gives us 11 minus 3, that is 8 units of time. And for P3, the turnaround time is 3 minus the burst time, that is 1. So what will that give us? 3 minus 1, 2 units of time. So for P4, turnaround time is 6 and then the burst time is 2. So that gives us 6 minus 2, 4 units of time. And the last one, P5, the turnaround time is 10 minus the burst time, that is 3. So that gives us 10 minus 3, 7 units of time. So here we have calculated the turnaround times and the waiting times for this set of processes. Now it is easy to calculate the average turnaround time and the average waiting time. So let's see how we do that. So the average turnaround time is 13 plus 11 plus 3 plus 6 plus 10 divided by the number of processes 5. That gives us 43 divided by 5, that is 8.6 units. And the average waiting time is 8 plus 8 plus 2 plus 4 plus 7 divided by the number of processes, that is 5, and that gives us 29 divided by 5, which is 5.8 units. So hence we have found the average turnaround time and the average waiting time for the set of processes P1 to P5 when they follow a round robin scheduling and when the time quantum is 2 units and when the arrival times are also given for this set of processes. So it may seem a bit lengthy to you, but actually I have just explained it in a very detailed way so that you may be able to understand it very clearly. So you can practice these problems more and more and it will help you to solve it quickly. And you just have to keep in mind that there are different things that we need to pay attention to when we are solving these problems on round robin scheduling. So as long as you keep that in mind and if you are careful enough, you will be able to solve these problems without any issues. So I hope this was clear to you. Thank you for watching and see you in the next one.
Okay, so that's it. Actually, this will be an example of round robin computations. Now, a while ago, we discussed already the characteristic of the round robin scheduling. And this time, this will be the advantages of round robin. So it doesn't face the issues of starvation or convoy effect. All the jobs get a fair allocation of CPU. It deals with all processes without any priority. So if you know the total number of processes on the run queue or key, then you can also assume the worst case response time for the same process. And this scheduling method does not depend upon burst time. That's why it is easily implementable on the system. Once a process is executed for a specific set of the period, the process is preemptive and another process execute for that given time period. Allow OS to use the context switching method to save states for preemptive process. And it gives the best performance in terms of average response times. And this will be the disadvantages of the round robin scheduling. And the worst case latency, this term is used for the maximum time taken for execution of all the tasks. So DT denote detection time when a task is brought into the list. ST denote switching time from one task to another. And DT denote the task execution time. And as what we have here, this will be the formula for worst case latency. Okay, so again, the round robin is the name of this algorithm comes from the round robin principle, where each person gets an equal share of something in turns. Round robin is one of the oldest, fairest, and easiest algorithms and widely used scheduling methods in traditional operating system. The biggest advantage of round robin scheduling method is that if you know the total number of processes on the run queue or key, then you can also assume the worst case response time for the same process. And this method spends more time on context switching. Worst case latency is a term used for maximum time taken for the execution of all the tasks. And that's it. Thank you for listening and attending our class. I hope that next meeting you are ready to take our quiz. Now covered all the CPU scheduling. Thank you and Godspeed everyone. Keep safe.